Swayam Prabha. Digital India. Educated India.
Welcome to the course on micromachining under DTH. Today I am going to talk to you about introduction to electrochemical micromachining. Electrochemical micromachining, acknowledgement, lecture on microelectrochemical machining delivered by Professor Bhattacharya, Jadavpur University, in the course on micromachining organized by IIT Kanpur. A chapter written by Professor B. Bhattacharya on electrochemical micromachining in the book on Introduction to Micromachining, Narasa Publishing House, Delhi. Thankfully acknowledge the help of Dr. Divyansh Patel, PhD scholar of IIT Kanpur, in preparing this lecture slides. There is a chapter also on ECM in the book on advanced machining processes, written by V.K. Jain and published by Allied Publishers, New Delhi. And then there is another lecture on advanced machining processes by V.K. Jain, lecture under the NPTEL program of Government of India. Course outline or outline of the presentation: electrochemical micromachining. You can have, or we are going to discuss theory of ECM process, Faraday's laws of electrolysis, material removal rate, self-regulating feature of electrochemical micromachining, equilibrium gap, and a single equation for gap evaluation. And then we are going to discuss electrochemical machining and electrochemical micromachining machine tool, power source, electrolyte cleaning and supply system, tool and tool feed system, work and work holding system. These are the things that we are going to discuss in this particular presentation. Introduction to ECM and ECMM, working principle of electrochemical micromachining, working principle of ECM and ECMM, that is electrochemical micromachining, remains the same, except that in ECMM the material removal or feature creation is at micro scale, that is dimensions are less than 1 millimeter, while in ECM it is at macro or meso scale, where the dimensions are greater than 1 millimeter. Electrochemical micromachining and overview. Electrochemical micromachining has very high potential of its applications in different fields, as we will see in this particular lecture. As ECMM process also works on the principle of Faraday's laws of electrolysis, in which a small pulse DC potential, usually less than 10 volt in case of ECMM, is applied across the two electrodes, that is cathode and anode, where anode is workpiece and cathode is a tool, which may be immersed in the electrolyte, or the flowing electrolyte may be supplied in the inter-electrode gap. In ECMM, usually pulsed DC power supply is used in place of a smooth DC power supply commonly used in ECM process. These days, however, many industrialists, they use pulse power supply in case of ECM also, because of its advantages. In ECMM, the transfer of electrons between the ions and the electrodes completes the electrical circuit. The metal is detached atom by atom from the anode surface and appears in the electrolyte as positive ions. The detached metal appears as precipitated solid of metal hydroxides. During the electrolysis of water, its molecules gain electrons from cathode, so that they separate into free hydrogen gas and hydroxyl ions. Working principle of ECMM, as you can see over here, these are the Faraday's laws of electrolysis based equation, where m is the mass proportional to ITE, where m is the mass of dissolved metal and E is gram chemical equivalent of the workpiece material, and which is given by AYZ. I is the current and T, small t, is the time. Now, this A is the atomic mass of anode material and Z is the valency of dissolution of anode material. So, in ECMM also we are using Faraday's laws of electrolysis as in case of ECM process. So, we have already seen m proportional to ITE, we can write it m is equal to EIT divided by F, where F is Faraday's constant and its value is 96,500 coulombs, where C is a coulombs. So, using the same equation as used in ECM, we can calculate material removal rate or amount of material removed in case of ECMM also. Let us see the schematic diagram of ECM as well as ECMM. Here you can see this is the cathode tool, this is the workpiece anode, and this is the electrolyte. Different types of the electrolytes are used in different while machining different types of materials. So, depending upon the type of electrolyte, reactions, chemical reactions may vary or will vary rather. So, here you can see hydroxyl ion is there and this is the metal dissolution from workpiece. Normally in case of ECM, 20 to 30 volt 20 to 30 meter per second is the flow velocity of the electrolyte at 2 to 35 kilogram per centimeter square pressure, and the voltage used is 5 to 20 volts. In some cases you can even go up to 30 volt in case of ECM. These are the input parameters I have told you. Input variables in ECMM same as in case of ECM. In ECMM, applied voltage is less than 10 volt, while in ECM, as I mentioned to you, it may be as good as 5 to 30 volts. Electrolyte flow velocity is normally less than 3 meter per second, current is less than 1 ampere, and inter-electrode gap varies 5 to 50 micrometer, and pulse power supply frequency is in terms of kilohertz to megahertz depending upon various requirements. So, electrochemical energy detaches metal from anode atom by atom. Electrochemical reactions, types of electrolytes used in ECM and ECMM. It can be acidic, it can be alkaline, it can be neutral depending upon the requirement. Reactions during ECM and ECMM with iron as anode and sodium chloride salt aqueous solution as electrolyte. So, these are the chemical reactions that are taking place. Electrolysis of water, H2O plus 2 electrons, hydrogen gas is evolved plus hydroxyl ions are there, then iron 2 Fe minus 2 electrons E is 2 Fe plus plus. Fe plus 2 OH, you have ferrous hydroxide. In some cases, in case of ferrous hydroxide, you can have ferric hydroxide depending upon the conditions in the electrolyte. Now, ferrous hydroxide and ferric hydroxide both are insoluble in water. So, positive ions convert as hydroxides, ferrous or ferric in case of iron as anode or workpiece material. Inter-electrode gap is less than 0.01 millimeter, voltage is less than 10 volt. Note it carefully, no electrolyte is being consumed in the process in this particular ECM as well as ECMM. Tool has theoretically infinite tool life because there is no dissolution from the cathode, that is the tool. So, theoretically it is infinite tool life, but because of so many other things, the tool life in ECMM as well as ECM are finite. Electrolytes. Electrolyte acts as a medium for current to flow between the electrodes. It takes away heat generated during the electrochemical reactions. We have already seen electrochemical reactions and heat is generated during them, and that heat is taken away by the flowing electrolyte. It removes reaction products etc. by flowing at high velocity in the inter-electrode gap. Sodium chloride commonly used as electrolyte, but there are other electrolytes also like NaNO3, KCl, NaOH etc. Recirculation of the electrolytes is done only after due filtration and till it maintains its electrical conductivity up to the designed one. Now, there are certain questions which you may ask, what is the importance of heat removal from the inter-electrode gap, because if you do not remove the heat quickly from the inter-electrode gap, the temperature of the electrolyte will change, and once the temperature changes, the electrolyte conductivity will change and you will not get the expected workpiece, shape, size, dimensions if electrical conductivity of electrolyte is changing during the ECMM process. And if you do not remove those sludge, that is the reaction products from the inter-electrode gap, they are going to contribute the change in the electrolyte electrical conductivity, which will affect the shape and size of the machine component. The electrolyte electrical conductivity may increase or decrease depending upon the type of sludge formed in the inter-electrode gap, and this is very important point. I will discuss it later on. Current density distribution in ECM and ECMM. Current density distribution depends on the inter-electrode gap, that is IEG. Smaller the inter-electrode gap, larger is current density, hence larger material removal rate, because as we have seen in the earlier slide that M is proportional to I, that is the current, and if you divide it by the area where current is flowing, then you get the current density. So, M is directly proportional to the current density. This principle holds true in case of ECMM process also. A smaller inter-electrode gap will lead to higher material removal rate because of lower gap resistance. Lower gap resistance, higher current will result in higher value of material removed in terms of micrometer, that is the thickness of the material removed, or it may be in micrometer cube, that is the volume of the material removed. As you can see here, wherever this is the workpiece and this is the tool, and you can see this is the inter-electrode gap, that is the distance between the workpiece surface and the tool surface. Now, you can see here this is the approximate replica of the tool that you are going to get, that is the final shape. Now, one important thing you can note here, wherever there is a smaller gap, more amount of material is being removed. As you can see, the gap here this much amount of material is removed, here only this is removed because the inter-electrode gap is larger here. So, we have already mentioned that smaller the gap, larger the current density, larger the material removal rate, and vice versa. As you can see here, wherever smaller gap is there, current density shown here by the lines, that is thicker one, and wherever larger gap is there, current density is smaller one. So, thinner lines are there. So, this is the workpiece, this is the tool. Material removal in ECMM process, part of current goes as a waste, and you can find in various books and research papers that the machining efficiency is ranging between 75 to 110%, especially in case of casting. So, you can be surprised that how come you have the machining efficiency larger than the 100%, but here there is a trick I have written here, especially in case of casting, which may be having the electrically non-conducting material. So, once the material surrounding that those particles is removed, those particles also come out without really consuming any current. Hence, you can get machining efficiency as greater than 100%. Inter-electrode gap is few tens of micrometers in case of ECMM process, and F is the feed rate, and this is the linear material removal rate. If feed rate of the tool towards the workpiece or vice versa is equal to the linear material removal rate, that is the in terms of microns or millimeter, then it maintains constant tool feeding to machine under equilibrium conditions. If you want to machine under equilibrium condition, you should maintain constant tool feeding. Tool life theoretically infinite, as I mentioned earlier, under ideal conditions. Now, let us see what are the various elements of electrochemical micromachining machine tool system. We start with schematic diagram of electrochemical machining setup. As you can see here, same elements are there in ECMM process setup or machine tool also. Now, you can see the voltage 2 to 30 volts. You can see here, this is the tool, this is the inter-electrode gap, this is the workpiece, these are the fixtures. Here the tool is insulated. Why? We will discuss little later. Here you have the heat exchanger. I have already mentioned that the temperature of the electrolyte is very important, so it should be maintained. Filter is there because this is the used electrolyte, so we should treat it properly before really recirculating it. So, you can see sludge is resting at the bottom, but the electrolyte after pumping you are filtering it in properly, then temperature is brought to the desired temperature, and then it is being supplied over here in the inter-electrode gap. This setup has been modified for ECMM at IIT Kanpur, that we will see later. Experimental setup designed and developed at IIT Kanpur by Priyadarshini and Anjali Kulkarni. As you can see over here, this is the setup that was designed and developed at IIT Kanpur for masters and PhD thesis work, research work. So, you can see here, this is the machining chamber is there, then electrochemical system cell is there, you have the exhaust system, this is the exhaust system going out, the fuel etc. that will be going out from here outside the chamber and outside the room even, and then you have the PC for controlling various activities of this setup, and then you have the power supply system, that is the 5 over here, and finally this is the schematic diagram of the same. Now, various things are shown over here. You can, as I mentioned earlier, you can use the DC pulse power or AC power supply system is used, microprocessor is there, then you have the stepper motor motion controller, because you have to control this is the tool over here. So, its motion has to be controlled properly. so that you have proper machining. So, to generate various types of the pulses, you can have rectangular pulse, triangular pulse, sinusoidal pulse. So, you have the function generator for that particular purpose. This is the tool holder, oscilloscope to view what type of pulses are being generated, you can see on the oscilloscope, and again function generator. So, this is function generator for the tool power supply, this is for the tool holder and other motions you are having another function generator, and this is the machining chamber, and these are the gases which are being evolved at cathode and anode, because we all know that hydrogen and oxygen gases are being evolved. So, electrochemical micromachining setup designed and developed at Jadavpur University, Kolkata by Professor Vijay Bhattacharya. Major elements of electrochemical micromachining setup: you have power source, you have electrolyte cleaning and supply system, tool and tool feed system, or you can have the feed to the workpiece also in place of feed to the tool, and then you have work and work holding system. Power source, rectifier converts and transformer transforms power supply to low voltage, that is 1 to 10 volt in case of ECMM, and voltage regulation can be achieved as good as plus minus 1%, because if voltage variation is there, then you will not get the accurately machined component, because voltage is going to vary the current supplied in the interelectrode gap, and that is going to change the current density, which finally affects the material removal rate at different locations. Electrolyte supply and cleaning system. This system consists of pump, filters, piping, control valves, heating, cooling coils, pressure gauge and reservoir. In ECMM, it is not necessary to make supply ports in tool workpiece. This is very important point. However, such ports decide the mode of electrolyte flow in the interelectrode gap, because in case of ECMM, tool sizes are in terms of few tens of micrometer itself, and to have the supply ports in such a small micro tools is very difficult. Hence, they have another way of using the electrolyte in case of ECMM. To maintain a small interelectrode gap, a few tens of micrometer, a smooth flow of electrolyte is a must, and there should be no blockade of interelectrode gap, otherwise the process may get stopped. Electrolyte flow velocity should be comparatively quite low to avoid any damage to the tool due to electrolyte pressure, because in ECM you have a very large, comparatively very large tool which can withhold or which can hold or which can bear the pressure of the electrolyte. But in case of ECMM, tool sizes are in few tens of microns and they may bend due to the electrolyte pressure, and very low velocity is used, or the tool and workpiece are submerged in the electrolyte, and on the other side of the tank of the electrolyte, a smooth and light flow of the electrolyte takes place. In some cases, anode may be immersed in the electrolyte and there may be no direct flow of electrolyte, as I just mentioned, because of the damage or the bending of the tool electrode. Electrolyte is supplied from top and taken out from bottom, having practically no pressure on the tool to avoid any damage to the tool during the process. Proper cleanliness of electrolyte is assured before its reuse by using filters made of anti-corrosive material. How that filtration etc. is being done by different systems, we have already seen in the earlier slides of Vijay Bhattacharya's setup. Electrolyte supply and cleaning cleaning system. You have filters which are periodically cleaned for proper functioning, and they are replaced in supply pipe just prior to the work enclosure. They are placed in supply pipe just prior to the work enclosure. Piping system is made of stainless steel, glass fiber reinforced plastic, plastic lined mild steel and other anti-corrosive materials that are used in fabrication. Metallic piping should be earthed to prevent anodic corrosion. Electrolyte supply and cleaning system again. Tables and fixtures are earthed and they carry cathodic potential to prevent corrosion. Electrolyte temperature is maintained within plus minus 1 degree centigrade. Heating or cooling is usually required, and they have the system to maintain the temperature of the electrolyte before it is supplied to the inter-electrode gap. Single tank system is normally used in case of ECMM machine. In general, in big industries, multiple tanks are used for ECM system, because ECM system uses very large amount of electrolyte and different types of the electrolyte depending upon the type of the workpiece material. So, they have multi tank system in big industries, say where turbine blades etc. are being machined and finished. But in case of electrochemical micromachining, normally that large amount of electrolyte is not used, and you normally have single electrolyte tank. For ECM and ECMM, both different metals and alloys will have different optimum machining conditions. This is very important, optimization of the machining conditions before really machining a part in the industries, and requirements of accuracy and surface finish will also be different. Modes of electrolyte supply. Electrolyte supply can be in one of the three modes: outward flow, inward flow, and outward and inward modes of flow are not recommended in ECMM, and in many cases they are not feasible due to very small size of the tool. Now, the question is, in the outward flow, electrolyte is supplied through a hole in the tool and exits through the side inter-electrode gap, and I have already mentioned that it is not recommended to make any hole in the tool, because tool size is so small that it may not be feasible in many cases to drill a hole within the tool of few tenths of micrometer size. Inward mode of flow, electrolyte enters through the side gap, side inter-electrode gap, and exits through a hole in the tool. Again, this is not recommended because hole drilling in micro tools is not that feasible. Side flow, electrolyte enters through the one side of the inter-electrode gap and exits from the other side of the inter-electrode gap. So, this is quite feasible and used in case of ECMM process, if you are having the flowing electrolyte. Otherwise, as I have mentioned earlier, that you have the electrolyte in the tank, you submerged to the workpiece and have the tool over there, and from one side of the tank you supply the electrolyte, on the other side you just take it. So, the flow velocity is very small in case of ECMM process. Electrolyte side and outward modes of flow. As you can see here, electrolyte is being supplied from one side, it goes out from the another side, and this is quite commonly used in case of ECMM process if you are allowing the flow of the electrolyte. Otherwise, as I mentioned earlier, tool and workpiece, they are immersed in the electrolyte, and electrolyte enters from one end of the tank and exits from the another end of the tank, and in that case the flow velocity is very small and you can easily control. sides of these tools are coated as you can see here with insulating material. Here you can see they are coated with insulating material, and here they are the bare tool. So, in case of this is also coated, as you can see from here, this is coated so that you have the constant inter-electrode gap and you can easily control it. However, coating of the tool in ECMM is a difficult task because of tool size, but it would help in achieving better accuracy. As you can see here, this coating is there and you get the constant inter-electrode gap. That means taper is avoided over here and you can easily control the dimensions of the workpiece. These insulations are there, but this noted carefully that this is basically for ECM process, because you are having the supply of the electrolyte through the tool and going out from here, but in case of ECMM process you cannot have such kind of the hole inside the tool easily, so that they are avoided. Tool and tool feed system. Tools are normally approximately inverse replica of the desired feature to be created. Please note it carefully, I have written approximately inverse replica. This is very important because you cannot get just the inverse replica of the tool on the workpiece, and that is why there is big importance of the tool design in ECM as well as ECMM process. We will discuss it later on. Desirable tool material, these properties, they should have high thermal and electrical conductivity, high thermal conductivity, so that the temperature of the electrolyte does not go high or does not change substantially, and electrical conductivity is required, so that flow of the current is proper and total requirement of the electrical energy is reduced. Anti-corrosive in nature, otherwise that will damage the workpiece as well as the tool, and high machinability, so that you can machine the or you can make the tool of the proper shape and size. Tool materials commonly used are aluminum, brass, copper, monil, bronze, etc. And types of the tool, they can be bare tool, coated tool, bit type of the tool. Again, this is very important for both ECM as well as ECMM, and I will show you different types of the tools little later. 3 types of the tools are there. You can see here, this is the bare tool. Anode profile obtained from using a bare tool, and you can see here there is no coating over there, and you find or you get the tapered side of the machine component, right. And if you see here, this is the bare, and if you see here, coating is there on this particular tool, coating is there, so that there is no flow or side flow of the current over here, as was taking over here and removing the additional material. So, here you can find this is the straight sided or straight side of the machine component of the whole, and you will have uniform gap over there. So, you can easily control the dimensions of the drilled hole or the machine component. So, that is the advantage of bare tool, and this is the anode and this is the cathode. Now, both of them are there, but in many applications, in place of having these tools made of electrically conducting material or metal, what people proposed long back is that you can have a bit type of the tool over here. This is the bit type of the tool, and rest of it is made of electrically non-conducting material, maybe plastics or other material, and this is made up of metal. So, you can see here clearly such a nice control of the inter-electrode gap and fully straight sided machine component is obtained over there, and this is highly recommended. It can also be used in case of ECMM process, where you have very small micro tools, and you can have this bit over there, and you can attempt to machine different kind of the components in case of ECMM process also. So, different parts are given over there. bare bit is there, and then we have the coated tool over there. Bit type of the tool is here, and then the workpiece is there. Stagnation zone is there, 5 is shown over there in different cases, and this is the stagnation zone 5 over here, or stagnation zone over here. And then front zone is there, this is very important. This is the front zone over here, 6. 7 is the transition zone, where you have the corner. You can see this is the transition zone, and then 8 is the side zone, this is the side zone over here, and then 9 is the tapered side. You can see here, this is the tapered side over here. And then you have the tool bit I have shown over here. Perspex tool bit holder, this is the Perspex tool bit holder, and then electrically conducting wires are there. These are the electrically conducting wires. So, these are the different types of the tools. They are very important, and they are commonly used in ECM process, especially the coated tool or the bare tool, but bit type of tools are also being used slowly in industries. So, insulation of tool bit type of the tool is better solution. Here also this tool bit partially you can insulate, so that this transition zone dimensions are controlled properly, but all that you have to work upon with the tool design. Accuracy and surface finish of tool affect workpiece accuracy and surface finish, especially in micromachining. So, please note it carefully. Surface finish is also going to affect the accuracy and surface finish of the final component in both ECM as well as ECMM processes. Tool and tool holder and workpiece fixture, you can see here. Tool holder and workpiece fixtures, electrically non-conducting material, sturdy enough to have minimum vibration and deflection under hydraulic force. As I have mentioned, in ECM you have the large hydraulic force, but in ECMM you have very small hydraulic forces. So, that you can check with this in case of ECMM. No change in dimension and strength due to immersion in electrolyte, and I have already mentioned that immersion of the tool and workpiece may take place in case of ECMM process, and no moisture absorption should be there either in the tool and workpiece, both materials. You can use GFRP, plastics, perspex, etc. for tool holder as well as workpiece holder, both, as I have given over here. Factors governing anode profile produced during ECMM process, that is, anode is the workpiece profile. Various process parameters for ECMM are given over here, as you can see here. Tool, conductivity of the tool material, stiffness, machinability. Voltage may be continuous or pulsed. Current, which affect cathodic reaction, pulse on, off time, also affect the whole process. Anodic reactions are also affected, and current density is affected by the magnitude of the current. And then you have the electrolyte, pressure, type of the electrolyte, concentration of the electrolyte, because concentration is going to govern the conductivity, electrical conductivity of the electrolyte, and the temperature is also affecting the electrical conductivity of the electrolyte. Then you have inter-electrode gap, that is the through which electrolyte is flowing and machining voltage is being applied across the inter-electrode gap. Now, what are the responses with the help of which you can evaluate the ECMM process? Machining rate, dimensions or dimensional accuracy, and surface finish. So, with the help of these three responses you can evaluate the performance of the ECMM as well as ECM processes. These parameters are the same as for ECM as well as ECMM process. Factors governing produced anode profile, as it continues, electrolyte properties, composition, concentration, temperature, etc., which will change in current density will affect the linear material removal rate. Voltage will affect the current density. For an alloy as anode material, use a mixture of electrolyte. This is very important, because most of the people are using single element electrolyte like NaCl or NaOH or NaNO3. But in case of an alloy as material, you can use mixture of electrolyte. It needs lot of research still to be done to find out appropriate mixture of the electrolyte to give the best performance in case of an alloy as anode material, because alloy has different composition, different alloys have different composition and they have different constituent metals which need different electrolyte to be machined, so that the material removal rate for different elements of an alloy comes out to be the same. For higher, it will result in higher accuracy and better surface finish. F is the tool feed rate in terms of millimeter per second or micrometer per second, depending upon whether it is ECM process or ECMM process. Tool shape and size, thermal conductivity, electrical conductivity and surface finish should be controlled. Gas evolution resulting in protective film affects over potential during the reactions, and factors governing anode profile produced during ECMM process. Let us see what are the functions of flowing electrolyte. It limits ion concentration at the electrode surface, and which will result in higher material removal rate. It dilutes the reaction products so that the change in the electrolyte's electrical conductivity is minimum during the machining process. It dissipates heats at a faster rate, so that again change in electrolyte conductivity is minimum because of this, and it permits flow of electric current between electrodes through the inter-electrode gap. Feed rate should be equal to MRRL, so that you can maintain constant inter-electrode gap, and constant MRRL, that is the linear material removal rate, is going to give you best accuracy of the machine component. Please note it carefully that if feed rate, tool feed rate is greater than linear material removal rate, there is probability of short circuit. If feed rate means tool is moving faster than the material is being removed, then short circuit may take place. That means the tool may touch the workpiece surface. If feed rate is smaller than linear material removal rate, then you will have higher inaccuracy and lower productivity or lower material removal rate. So, one should try to machine in ECM as well as ECMM under the equilibrium condition where feed rate is equal to linear material removal rate. Now, what are the applications and ECMM operations? Electrochemical micromachining operations, you can have electrochemical micro drilling, electrochemical micro deburring, electrochemical die sinking with micro features, electrochemical grinding, electrochemical honing, electrochemical micromachining, electrochemical micromilling, electrochemical micro sawing, electrochemical micro turning ECMT, electrochemical micro trepanning, electrochemical wire cutting. Please note it carefully. While I am using the word process, this is very much different from the operations. Here the process is electrochemical micro machining, but these are the different kind of the operations that are being performed or that can be performed using this particular process. Note, feature created should have at least one dimension in micrometer, in micron, to be called as electrochemical micromachining operation. That means the one dimension should be less than 1 millimeter, so that you can write it in terms of few hundred or few tens of micrometer, then only it will be called as electrochemical micromachining operation. Some electrochemical micromachining operations are here. You please see it carefully. This is the electrochemical boring. As we all know, in boring we are increasing the dimension of the drilled hole already. So, this is the drill hole and this is the tool, and you are feeding the tool, so that you are really increasing the diameter of this drill hole to this particular drill hole with the help of electrochemical boring operation. And you can see here electrolyte is shown over here, tool feed is shown over there. This is the enlarged view of this particular small part. Now, here you can see work rotation is shown. For having a better accuracy in case of electrochemical boring operation, you can rotate the workpiece, so that you can have uniform diameter of the bored hole. Then electrochemical deburring, very important operation. Now, burrs are being formed when you have conventional drilling process, conventional machining process, conventional milling process. Now, how to remove those micro burrs? So, you can use electrochemical micro deburring process, and this is the tool, this is the micro burr, and electrolyte is flowing. So, dissolution of these burrs will take place, and you will have a well cleaned surface or edges without any burrs. So, you can have a stationary rotation of tool is optional, whether you have the stationary tool or rotating tool, depending upon your requirement and feasibility. Now, this is electrochemical grinding. We will discuss these processes later on in detail. You can see over here, this is the workpiece, this is the grinding wheel, and you can see enlarged view of this part. These are the abrasive particles, and this is the electrolyte. So, abrasive particles are responsible for grinding operation, and this gap between the two and electrolyte, they are responsible for electrochemical micromachining operation. And you can see, that is why it is known as electrochemical micro grinding or electrochemical grinding. I have not used the word micro, because all these operations are at micro level or nano level. Here you have the electrochemical trepanning operation shown over here. This is the tool, and you are machining all around this, so that this part will come as a solid part. So, you remove only this much of material which is shown over here, and this is how you can perform electrochemical trepanning operation, just like a trepanning operation done conventionally with the help of trepanning tool. So, this is the trepanning tool, which is the top view shows over here the tool, and you move it like this and you will get it. Electrochemical micromachining, other operations are there, very interesting. Electrochemical turning operation is there, you can use it as micromachining, micro turning also. Here the feature that you may create should be the in terms of microns, so that this feature is in micron, this is also going to be in terms of micron. This can be like this and this can be like this. You are giving the feed in vertical direction, and the workpiece is rotating, and here you are supplying the electrolyte through this. So, just like in turning operation, you are rotating the workpiece, tool is stationary, same way here tool is stationary, workpiece is rotating, and in the interelectrode gap electrolyte is being supplied. Here you can see tool is negative, that is the cathode, and workpiece is anode, that is the positive. You can have electrochemical wire cutting. This is the wire that is being used, and you can see here this is cutting. I have shown here larger view, larger dimensions, because so that they are easily visible. Now, if it is wire cutting, general wire cutting, where you have the wire diameter, very large wire diameter, then you can supply the electrolyte through the wire, and it will be taken out from here. Here you have the holes over there. But in case of electrochemical micro wire cutting, if the dimensions of the wire are in terms of micron, then you have to supply the electrolyte separately, not like this. You have the electrochemical sawing operation, it can be micro sawing or sawing operation, depending upon the cut you are making over here. This is the cutting of wheel, which is definitely electrically conducting material over there. Electrolyte is being supplied over here, and it is rotating, wheel is rotating. So, you are able to make the micro cut over here and make 2 pieces of this particular workpiece, and these are the very hard workpiece material which you cannot you cannot cut it conventionally so easily. And then this is the shaved tube electro machining system, STEM it is being used. Now, you can perform this at micro level also. You can see clearly over here, these are the tube, electrolyte is being supplied and you are moving it downward and you are cutting it inside this one. So, to be called as ECMM operation, one machine dimension should be in the micrometer range. Design and development of micro tools. You can see over here, this is the uninsulated micro tool, this is the insulated micro tool, this is the dual pole machining accuracy. You have both poles, this is the this is the cathode and this is the anode, and electrolyte is being supplied from there, and this is the workpiece which is again anode. So, this is one, you can have fabrication of micro tool, this is the one, and these dimensions are in terms of few tenths or few hundreds of microns depending upon your requirement. You have to design the size, shape and profile of the tool. You can use wire EDM process, reverse EDM process or ECM process for making these micro tools. And coating as shown over here or shown over here, you can use CVD, sol gel etc. or dual pole tool also can be used. I have shown dual pole tool over here. This is the anode and this is the cathode on the same tool. Now, how to prepare micro tools? These are the some commonly used processes for preparing micro tools. This is the block, this is the micro tool being prepared. You are rotating this micro tool and feeding it upward and downward, and this is the one stationary sacrificial block. You can use either ADM process or ECMM process. This is the rotating sacrificial disc. This is again micro tool being prepared, moving up and down and rotating, and this is the disc which is again electrically conducting. You can use EDM process for this, and thickness of this disc is 0.5 micrometer, that is 500 micrometer. 0.5 millimeter, that is 500 micrometer, or you can use wire EDM process or wire ECM process. This is the micro tool being prepared, and you can have either dielectric or electrolyte depending upon which process you are going to use. Advantages of electrochemical micromachining process. It can machine complicated shapes in single pass, quite different from other processes like Liga and others, because Liga involves so many steps before really you are able to machine or prepare a part. But in case of ECMM, it is a single step process, which is a big advantage compared to other processes. Now, machinability is independent of physical and mechanical properties of the workpiece. Physical and mechanical properties of the workpiece like hardness, toughness or other magnetic properties or corrosive nature, they are not affected as long as machinability is concerned. And then you are going to achieve stress and burr free components are obtained after ECM and ECMM process, because in case of EDM process or other processes you get the thermal stresses over there. In case of conventional processes you get the burrs etc. So, both of them are absent in case of ECM as well as ECMM process, and you achieve good accuracy, low scrap, automatic operation. It also permits the machining of chemically resistant materials like titanium, copper alloys and superalloys, which are widely used in biomedical industry, electronic industry and MEMS applications. Now, let us see the limitations of the process. Only electrically conductive workpieces can be machined. Accuracy is the function of tool design, degree of process control, shapes, complexity, etc. Difficulties are there because of hard spots, sand inclusions, sharp corners and edges, and they are really difficult to machine accurately, and because these are hard spots and sand inclusions, they are electrically non-conducting, so they cannot be machined. What we have done in this lecture, that is ECMM part 1. Let us quickly see what is ECMM and how it is different from ECM, that we have seen over there. Faraday's laws of electrolysis, experimental setup of ECM and ECMM and its elements, different types of ECMM operations, and how to make micro tools using EDM, EDAG processes, as well as you can use ECM and ECG processes also. Merits and limitations of ECMM process. This is MET, it is MERITS, not METITS. Thank you very much.